Okay, so I want to start by thanking the organizers for giving me the opportunity to speak here at this workshop. I'm going to talk about this work done in collaboration with my PhD student, Diogo de Souza. He's going to be in the market next year or so, so please consider him as a postdoc. He's very good. And this is a paper that is going to appear shortly in Physical Review D. And the title is, Can Neutrino-assisted early dark energy models ameliorate the H-naught tension in a natural way? So it's a mouthful, and I want to explain what do I mean by this title. And of course, you know what the answer is, right? There's a theorem that every article that has as a title a question, the answer is no. And this is, you can check, this is really the case. So this is, you know the answer is no. So before starting talking about this, I want to say a little bit about, some of you may already know, but we have in São Paulo a kind of a branch of the the ICTP, which we call the South American Institute for Fundamental Research. So I want to spend 2 minutes doing some advertisement about this center. If I can change this. Everybody's fine. Okay, how should I change this? Like that? Huh? Click the mouse once. Okay, thank you. Okay, so so we have lots of activities in this institute. It's based in São Paulo, and we offer activities for grad students, undergrad students, but especially for PhD students. So we have schools, we have workshops, etc. We just had a public lecture by David Gross. We had a colloquium by Nima Kani-Hamed, a school of modern amplitude methods for gauge and gravity theories. We are going to have, if you're interested, a school, oh, it's not here, it's in November. We're going to have a school on baryogenesis, which I really recommend to students that want to apply. It's a 2-week school. It's organized by Geraldine Sylvain and other people, and Shaposhnikov is going to be there. So it's really a good school. And the application deadline is September 10. So just go to the page here of our page and check for this for the activities. We're going to have a cosmology workshop, but this is at the end of next year. I also want to advertise that. So yeah, so we have plenty of activities. Please go to the webpage, and we have no registration fee for any of the activities, which is really good. And furthermore, the students that are accepted, they get support for local costs. So everything is covered locally. So this is really a great deal. It's funded by the, basically it's funded by the state of São Paulo. So, okay, this is the end of my advertisement. So let me talk about this work. So of course, you all know about the Hubble tension, which is a tension between the determination of the Hubble constant from the CMB and from local measurements. This is a plot that I took from this review paper of Adam Rees. So this is a very hot topic, as you probably know. There are many attempts to reconcile CMB with local measurements. Of course, I forgot to say, it could be, I forgot to say that, no, you probably know that the discrepancy is around 5 sigma-ish, but we don't know if these are systematic errors or if it's new physics. So of course, the exciting thing for me and for other people is if this is new physics. And if it is new physics, it's the first maybe crack in the lambda CDM model. And there are attempts to reconcile the CMB, the early data, with local measurements using new physics. For instance, if there is an extra contribution to the energy density of the universe, which means a faster expansion rate with respect to lambda CDM, so with respect to the standard cosmological model around the recombination era, that keeps the angular scale of the CMB peak fixed, this would require a larger value of H0. So this would result in a larger value of H0 from the CMB measurements, and hence a better agreement with the local measurements. So you could have new relativistic degrees of freedom, or something called early dark energy, which I'm going to talk about, decay in dark matter. In fact, there are many, many models that try to reconcile these early and late measurements of the Hubble constant. And So this is a plot also I took from Rees. If you have a new physics, these are different new physics, a change in the equation of state, a change in the effective number of the relativistic degrees of freedom, curvature, etc. You can have a shift from the Planck results, from the CMB results, to not quite here, but you decrease the tension. And in fact, I just show this. This is from a review. Some of the authors are in the audience here about possible solutions to this tension in H0. So there are many, many models, and these authors classify in excellent models, good models, and promising models. And early dark energy is one of these, they call it the excellent models. Okay, so a few words about early dark energy. What is early dark energy? So the main idea is that some amount of what we call dynamical dark energy, which for us is basically a scalar field moving a potential, contributes a non-negligible amount of energy density at around recombination, and then change the expansion rate, and it decays away afterwards in order not to change the late time cosmology. And this was proposed first, I think, by Tanvi Karwal and Marko Minkowski in 2016. And there are now many, many papers about the early dark energy. Very generally, there are two relevant parameters that one may consider in this type of models. One is the redshift, where the early dark energy, which I'm calling EDE, peaks. So this is usually called the Z sub C. And then the fraction of the early dark energy at the peak, which is usually called FEDE. So this is the fraction of early dark energy with respect to the total energy density at this peak contribution. So those are the two main parameters that one might consider. And this is what I'm going to discuss in this talk also. So just to give an idea, this is a plot that actually another student of mine, João Rebouças and some collaborators did using, okay, this is a whole different talk. I'm not going to give it now, but this is just to show you that this is a plot. This is a Markov-Chain Monte Carlo using different data, including data from clustering of galaxies, but it doesn't matter. The only thing I want to show you is that there is this plot of FEDE at the maximum as a function of the Hubble constant. And you can see that you can actually go towards lower values if you have EDE of the order of 10%. So you can go to, you can agree more. This does not include the this includes CMB, but you can get better agreement if you go to like 7%, 8% contributions of early dark energy. Okay, so how do you model early dark energy? You model with a scalar field, as I mentioned before. The scalar field depends on the potential. This is a prototypical potential, axion-like potential. Doesn't really matter much. So it's fixed by this power n, and there's a small energy scale, which is related to explicit breaking of some shift symmetry. There's a large energy scale, which is related to spontaneous breaking of a global symmetry. And n equals 1 is the axion potential, exactly the axion potential. Also depends on initial conditions for the field. So early dark energy, as I mentioned before, has to decay after recombination. How does it decay? Well, this is why we have this power n here. Sorry, what did I do? Can I go back? Yeah. So this is why we have this power n here, because depending on n, this field, when it starts to oscillate around the minimum, it behaves like a fluid with an equation of state given by this thing here, n-1 over n+1. So if n is larger than 2, the early dark energy decays faster than radiation, then quickly becomes negligible. So in usual models, people assume n equals 3. And so the thing is that the usual early dark energy models, they have a coincidence problem. What is the coincidence problem is why early dark energy becomes relevant exactly around the recombination epoch, not before, not very much after. And there's no good answer for this usually. people just assume a fine-tuning of parameters, and we don't think this is really satisfactory. So a generalization of this early dark energy model was proposed recently to address this coincidence problem. And this is called the neutrino-assisted early dark energy. It was proposed in this paper, Sexton and Crowden in 2019, and there are other studies afterwards. So I'm going to concentrate on this model, and I'm going to explain why this model, in principle, ameliorates this coincidence problem. So what is neutrino-assisted early dark energy? It's a mouthful, so we call it NEW-EDE. So NEW-EDE postulates a coupling between neutrinos and the scalar field responsible for the early dark energy. We denote this coupling by beta. And there are two main effects of this coupling. First is that the scalar field is not it's moving in effective potential, it's time-dependent potential because of this coupling. So it's not only the potential I wrote before, but has an extra contribution, which is proportional to the density of neutrinos. And the coupling to neutrinos also, this is very interesting, induces a kick in the field. So how does it do it? It does it the following way. So the neutrino kick, it happens because the coupling of the neutrinos to the early dark energy field turns out to be related to this relation, rho nu, the energy density neutrinos, minus 3, the pressure of neutrinos. For those that are familiar, this is the trace of the energy momentum tensor of the neutrinos, but it doesn't matter. So this thing here, it is 0 for relativistic particles, and hence the coupling disappears. And it turns on when neutrinos transition to relativistic to non-relativistic. So this is the kick that happens at this around the time when neutrinos become non-relativistic. And this happens at around the mass scale of neutrinos, which is around the electron volt scale, which is actually the same scale. By coincidence, it's around the scale of recombination. So this is how it solves the coincidence problem. So what we did in this paper is that we investigate this model in more details, and we assess to what extent the coupling to neutrinos can really help in the fine-tuning problem. How did we do that? We implemented these NEW-EDE models in CAM at the background level to analyze the evolution of the scalar field in the time-dependent effective potential, given some initial conditions and some model parameters. So that's what we did. So basically, we solved the equations of motion, so the Klein-Gordon equation, for the scalar field in the presence of the background neutrinos in the effective potential. Okay. So we studied two cases for the initial conditions. One where the field is starting with the field starts at some arbitrary value, and it's initially frozen by Hubble friction. And the other case, which is more natural, and there's this word natural in the title of this paper. So we want to do something more natural, which is the field starting at the minimum of the effective potential. So the field is already relaxed to the minimum of the potential, it's dynamical. So in the second case, the neutrino transition would give a kick to the field from the minimum, and then would solve the fine-tuning issue because the kick would happen around the time of recombination. So that's the idea. Okay, so some results. This is just an example of the energy density of or the fraction of energy density in the early dark energy. So this is the usual plot that you've seen several times of the fractions of energy in different components. And I want to call your attention to this bump here. So this is the scalar field, which is the early dark energy that's happening. So we still need the cosmological constant. So that's why we have lambda here. But this is due to the early dark energy field. So there is a bump here with the parameters that we chose to make this plot, which is around 0.7, 0.8%. However, what we show in this plot here in the lower plot is that this is not due to the coupling, because this is the ratio between this fraction with the coupling equals 0, but this is due to the initial conditions. So this does not solve the fine-tuning problem. So this is also an example of the early dark energy field evolution in the effective potential for different initial conditions. So here are the initial conditions at some redshift 10 to the 5, and the field is frozen. This is the case where the field is initially frozen. So you see that it's frozen until it thaws, the field thaws, and then it follows the minimum of the effective potential. The minimum of the effective potential is this black dots here. And you see that then it oscillates around the minimum of the effective potential as it should. So this is an example of how is the dynamics of this of the area dark energy field when you have this coupling, which induces this effective potential. So this is another, again, this is now the results for the dynamics of the field. So this is another plot for the dynamics of the field for different initial conditions. And again, you see that you can generate, not very difficult to generate a peak of around 9–10% of FED. But again, what I want to stress is that this is not due to the coupling to neutrinos. This is just due to the initial conditions. How do we know that? Because here you can barely see, but there's a dashed line, and the dashed line is on top of the continuous line, and the dashed line is when you put the coupling of neutrinos to 0. So it basically doesn't change anything when you couple with neutrinos in this case. Now, now we want to show what happens if we choose the conditions such that the field is already relaxed to the minimum of the effective potential. So here's evolution of the field, and we start with different initial conditions, but then the idea is that at a z equals 10 to the 4 or so, it already follows the minimum of the effective potential. So these lines here, the dashed lines, the black lines are the minimum of the effective potential, and these are the initial conditions, and they follow. After some time, they follow the minimum of the effective potential, and this avoids the initial condition issue because we can show is that it doesn't matter what is the initial condition, it will end up following the minimum of the effective potential. And this would be the natural solution to the coincidence problem, in our opinion. So in this case, the neutrino coupling is relevant and produces a large enhancement in the early dark energy density. Here is a plot showing the difference between this fraction of early dark energy with and without the neutrino coupling, and we see that there is a huge enhancement, which is due to this motion of the field around following the minimum of the effective potential. So you would think this will solve the problem, but if you notice, FEDE is very small in this case, and this is what we found. We found that the amount of early dark energy is insufficient to solve the Hubble tension or even to improve. So these are the plots of the fraction of early dark energies for different values of the parameters. The lines here in the middle are the analytical estimation that we can make, and these oscillations here are the numerics. So the analytical is the average of the numerics, and you can always see that you cannot reach FEDE, which is relevant for solving the Hubble tension. So that's the conclusion. The neutrino early dark energy models do not seem to naturally provide a significant amount of early dark energy, which is one of the criteria that is usually required for the model to ease the Hubble tension. However, and this is a grain of salt that we should add always, is that one should perform a more detailed study using a full Bayesian analysis to take into account not only the peak contribution of early dark energy, but also the contribution outside the peak. And also one should study, of course, other types of potentials and couplings to make make a clear case that this cannot help the Hubble tension. However, this work I think is indicative that neutrino early dark energy models cannot, at least the simplest models, cannot naturally provide a solution to the Hubble tension. Thank you.